Embarking on a journey through the cosmos, we find ourselves entangled in one of the most profound mysteries of modern astrophysics, dark matter. This elusive substance, invisible to our current observational instruments, is believed to constitute approximately 27% of the universe's mass and energy. Unlike normal matter, which makes up stars, planets, and even us, dark matter does not emit, absorb, or reflect light, rendering it virtually undetectable through direct observation. The concept of dark matter was born out of an astronomical conundrum. In the 1930s, the Swiss astrophysicist Fritz Zwicky observed that galaxies in clusters were moving much faster than they should be, based on the gravitational pull of their observable mass alone. This discrepancy suggested the presence of some unseen mass exerting an additional gravitational force, what Zwicky referred to as dunkle materie, or dark matter. Further evidence for dark matter emerged from observations of galaxy rotations. According to the laws of physics, the speed at which stars orbit the center of their galaxy should decrease with distance. However, when astronomers observed galaxies, they found that stars on the outskirts were orbiting just as fast as those near the center, a phenomenon that defied explanation unless there was additional unseen mass in the galaxies. This invisible mass seemed to form a halo around galaxies, influencing their dynamics and structure. Another intriguing aspect of dark matter comes from the phenomenon of gravitational lensing, the bending of light from distant objects by massive foreground galaxies. The degree of bending observed in these cases indicates far more mass than can be accounted for by visible matter alone. In essence, dark matter acts as a cosmic magnifying glass, altering the path of light through the universe. The precise nature of dark matter, however, remains a tantalizing mystery. The leading hypothesis is that it is composed of weakly interacting massive particles, which barely interact with regular matter. Other theories propose candidates like axions or sterile neutrinos, particles that are fundamentally different from those found in the standard model of particle physics. The pursuit of dark matter has also led to the development of highly sensitive detectors buried deep underground or submerged in water or ice. These facilities aim to shield experiments from cosmic rays and other forms of interference that could mimic the elusive signals of dark matter particles. The notion that dark matter could serve as a conduit for extraterrestrial communication is a thought-provoking intersection of astrophysics and the search for intelligent life. This theory springs from the idea that an advanced alien civilization, far beyond our current technological capabilities, might utilize the properties of dark matter to communicate across the vast expanses of space. But why dark matter? The answer lies in its ubiquitous presence and its unique, enigmatic properties. Dark matter, by its very nature, does not interact with electromagnetic radiation, the cornerstone of human methods of communication such as radio waves. This means that messages encoded in dark matter wouldn't suffer the same fate as electromagnetic signals, which dissipate and lose their strength over interstellar distances. Furthermore, dark matter isn't hindered by cosmic dust or other interstellar matter that can absorb or scatter electromagnetic radiation. Hence, it stands as a potentially more efficient medium for long-distance communication in the cosmos. The challenge, however, lies in the theoretical framework and technological advancements required to harness dark matter for communication. If dark matter is composed of WIMPs, these particles might interact with regular matter through gravity or weak nuclear forces. An advanced alien civilization could theoretically manipulate these interactions to encode information. This process would be akin to modulating a carrier wave in radio communication, but on a far more subtle and complex level. Moreover, the potential of dark matter communication opens up new realms in our understanding of the Fermi paradox. The apparent contradiction between the lack of evidence for extraterrestrial civilizations and various probability estimates for their existence. It's conceivable that alien civilizations are using dark matter to communicate, and humanity's current technological limitations prevent us from intercepting or understanding these communications. Our focus on electromagnetic signals may be the equivalent of listening for a whisper in a world where other civilizations are using a different form of sound altogether. Another fascinating aspect to consider is the stability of dark matter signals. Unlike electromagnetic signals, which can be altered or disrupted by various cosmic events, dark matter remains largely unaffected by the universe's dynamism. This stability could make it an ideal medium for not just communication, but also for storing information over cosmic timescales. However, the use of dark matter for communication remains purely speculative, as our understanding of dark matter is still in its infancy. Our current experiments and observations are geared toward detecting dark matter and understanding its properties, rather than manipulating it for communication. Delving into the cosmos's enigmatic corners, we encounter a fascinating and speculative idea. Could life forms exist that are composed of dark matter? This notion challenges the very foundation of our understanding of life and its necessary conditions. The concept of dark matter life stems from the fact that dark matter, which makes up a significant portion of the universe's mass, interacts with gravity but remains virtually undetectable in other ways. This invisible and enigmatic nature of dark matter raises the question, could there be entities, perhaps even entire ecosystems, that are based on dark matter instead of the baryonic matter that constitutes the known life on Earth? To explore this idea, let's first consider what we understand about life. On Earth, life is carbon-based, relying on water and a complex chemistry involving a handful of elements like carbon, hydrogen, oxygen, and nitrogen. However, the universe is vast and diverse, and the possibility that life could develop based on entirely different principles cannot be entirely dismissed. If dark matter life exists, it would likely be radically different from anything we know. These hypothetical beings would not interact with light, making them invisible and intangible to us. They could be living right beside us, yet completely undetectable with our current technology and methods. The intriguing part about dark matter life is how it might interact with its environment. Since dark matter does not interact electromagnetically, the conventional notion of biology, involving absorption of light for energy or chemical reactions, would not apply. These life forms, if they exist, would have to rely on an entirely different set of principles for their metabolic processes. They might utilize weak interactions or gravitational effects to sustain themselves. This raises fascinating questions about their structure, reproduction, evolution, and even consciousness. Astrophysicists and biologists have pondered over this, and some theories suggest that dark matter organisms could exist in a parallel realm, only interacting with our world through gravity. These interactions could potentially explain some of the unaccounted gravitational anomalies observed in the universe. Moreover, the concept of dark matter life forms extends beyond the realm of biology into the realm of astrobiology and the search for extraterrestrial intelligence, SETI. If life can exist in a dark matter form, it broadens the scope of SETI to look beyond traditional signals like radio waves or visible light. Perhaps these life forms have developed their own means of communication and society, which we are yet to comprehend or detect. The pursuit of dark matter has propelled scientists into a new era of technological innovation, as they endeavor to detect something that neither emits nor absorbs light and has eluded direct observation. This quest has given rise to an array of sophisticated experiments and detectors, each designed to catch a glimpse of this mysterious substance that is believed to permeate the universe. One of the forefront technologies in this pursuit is the use of underground laboratories. These facilities, like the large underground xenon experiment in South Dakota and the Gran Sasso National Laboratory in Italy, are located deep beneath the Earth's surface. The depth is crucial, as it shields the experiments from cosmic rays and other forms of background radiation that could interfere with the detection of dark matter particles. Inside these labs, detectors are immersed in fluids like xenon or argon and maintained at incredibly low temperatures. The hope is that as dark matter particles pass through these detectors, they will collide with the nuclei of the atoms in the fluid, producing a flash of light or an electrical signal that can be measured. Another promising technology is the use of space-based detectors. Unlike ground-based observatories, these instruments can search for evidence of dark matter particles from orbit, free from the Earth's atmospheric interference. The Alpha Magnetic Spectrometer, also known as AMS, installed on the International Space Station, is one such detector. It searches for indirect evidence of dark matter, such as the presence of specific particles that could be byproducts of dark matter collisions or decay. In addition to these experimental setups, advancements in particle accelerators have also played a significant role. The Large Hadron Collider at CERN, the world's largest and most powerful particle accelerator, has been conducting experiments that could provide insights into the properties of dark matter. By colliding particles at high energies, scientists hope to create conditions that could briefly produce dark matter particles, allowing us to study their properties and interactions. One of the intriguing aspects of these experiments is the search for weakly interacting massive particles. WIMPs are a leading candidate for dark matter, as they would only interact weakly with ordinary matter, explaining why they have been so difficult to detect. However, despite years of searching, WIMPs have remained elusive, leading some scientists to consider alternative candidates, such as axions or sterile neutrinos. The technology used in these searches must be incredibly sensitive, as the interactions between dark matter particles and baryonic matter are expected to be rare and subtle. This sensitivity makes the experiments vulnerable to even the slightest environmental or instrumental noise, requiring innovative solutions to isolate the detectors from potential sources of interference. As we delve deeper into the cosmos, the role of dark matter becomes increasingly significant and fascinating. This mysterious substance, which does not emit, absorb, or reflect light, plays a crucial role in the grand cosmic ballet. Despite being invisible, dark matter exerts a gravitational pull, influencing the motion of galaxies and the structure of the universe at the largest scales. One of the most profound roles of dark matter is in the formation and evolution of galaxies. The current understanding among astronomers is that dark matter acts as a cosmic scaffolding around which galaxies are built. In the early universe, dark matter would have begun to clump together under its own gravity, forming a web-like structure. These dark matter concentrations created gravitational wells that attracted normal baryonic matter, leading to the formation of stars and galaxies. Without the presence of dark matter, the gas in the early universe would not have had enough gravitational pull to coalesce and form these structures. Dark matter also plays a pivotal role in holding galaxies together. When astronomers observe the rotation of galaxies, they find that the stars at the edges of galaxies are moving just as fast as those near the center, contrary to what would be expected if only visible matter were present. This observation suggests that something unseen, dark matter, is providing additional gravitational force binding the galaxies. Without dark matter, galaxies like our own Milky Way might not have been able to maintain their present form and could have been torn apart by their own rotational speed. Furthermore, dark matter is essential in understanding the overall structure and fate of the universe. It is a key component in the Lambda CDM model, the standard model of cosmology that describes the universe as composed of dark energy, dark matter, and normal matter. The interactions and relative proportions of these components determine the rate of expansion of the universe and its ultimate fate. Dark matter's gravitational pull works against the repulsive force of dark energy, which is accelerating the expansion of the universe. This interplay is a critical factor in cosmological models that predict how the universe will evolve over billions of years. The study of dark matter also intersects with other areas of astrophysics, such as the study of gravitational lensing. This phenomenon, where light from distant galaxies is bent around massive objects, provides indirect evidence of dark matter. The amount of lensing observed in these instances is far greater than what would be expected based on visible matter alone, reinforcing the theory that dark matter is present and abundant in the universe. In cosmic voids, large, empty spaces in the universe where few galaxies exist, dark matter plays a subtle yet important role. These voids are not entirely devoid of matter but contain small amounts of dark matter, influencing the motion and distribution of galaxies at the edges of these voids. Have you ever gazed at the night sky and wondered if there's intelligent life out there? And if there is, wouldn't it be absolutely fantastic to meet them, perhaps for an intergalactic coffee or just some good old cosmic banter? Well, not so fast. Today we're diving deep into the theories and ideas of why meeting extraterrestrial life might not be the best thing for us. The vastness of our universe is truly mind-boggling. With billions upon billions of stars, many of which have their own planetary systems, the question arises, where is everyone? Why haven't we found signs of intelligent life? Or why haven't they found us? This puzzling conundrum, sometimes referred to as the Fermi Paradox, poses the question, if the universe is so big, shouldn't there be evidence of intelligent life out there? Enter the Great Filter Theory. This theory offers a possible solution to the Fermi paradox. It suggests that there's a stage or multiple stages in the evolutionary process of life that act as a sort of bottleneck, preventing species from further advancing or even causing them to go extinct. Imagine the path to cosmic intelligence as a series of steps. These steps could include the formation of planets, the emergence of simple life, then complex life, the development of intelligence, and eventually the creation of technology capable of cosmic communication or travel. If every one of these steps was easy and inevitable, our universe should be teeming with life. However, the Great Filter theory posits that one of these steps, or perhaps more than one, is incredibly improbable. It's a filter that prevents most potential life from advancing to the next stage. Now, this theory can be both comforting and unsettling. If the Great Filter is behind us, perhaps in the leap from non-life to life or from simple to complex organisms, then we might be one of the few, if not the only, civilizations that made it through. That would mean the universe is ours to explore with little worry about encountering advanced alien civilizations. On the other hand, if the Great Filter lies ahead of us, it means our civilization is headed towards some insurmountable challenge. This could be anything from self-destruction via war, catastrophic environmental collapse, or any other number of unforeseen challenges that have doomed other civilizations before us. In the realm of interstellar interactions, a fascinating concept emerges, one that reflects past human histories, the Dependency Paradox. When two civilizations of vastly different technological levels meet, there's a chance that the less advanced society becomes heavily reliant on the superior technology of the more advanced civilization. Drawing parallels from our own history, when indigenous communities encountered technologically advanced colonizers, they were often introduced to new tools, weapons, and methods that, while advantageous, led to a dependency. Traditional skills and techniques passed down through generations were quickly abandoned in favor of the new technology. But this shift came at a cost. These societies became vulnerable, losing autonomy and self-sufficiency. Now let's elevate this scenario to a cosmic scale. If humans were to depend heavily on alien technology, we might experience a profound societal change. The rapid introduction of such superior tech might lead to the abandonment of our own innovative pursuits. Why invent or innovate when technology from a more advanced civilization is readily available? Furthermore, with dependency comes vulnerability. If for any reason the advanced civilization withdraws or restricts access to their technology, the less advanced society, in this case us, might find itself in a precarious situation. Societies, infrastructures, and systems built upon and adapted to the alien technology might collapse or malfunction without it. Additionally, such a dependency could have profound psychological effects. The sense of inferiority, the loss of self-reliance, and the overshadowing of human achievements by alien wonders might lead to a collective identity crisis. Who are we in a universe where our accomplishments seem trivial compared to those of extraterrestrial beings? The universe, vast and teeming with endless possibilities, may harbor civilizations that, should they ever cross our path, might have intentions that are difficult for us to fathom. The intentions of an alien species, especially one that can traverse galaxies and has advanced far beyond our comprehension, are a pressing concern in any potential first contact scenario. When we reflect upon our own history, encounters between societies of differing technological levels rarely ended favorably for the less advanced culture. Often, such meetings were characterized by conquest, resource extraction, or unintentional harm, such as the spread of diseases. If our history is any lesson, it's that the balance of power and intent plays a significant role in the outcomes of first contacts. Now think about a civilization advanced enough to reach our planet from the distant corners of the cosmos. The sheer technological prowess required for interstellar travel would indicate capabilities beyond our understanding. But technology alone doesn't dictate intentions. While it's hopeful to imagine that any society which has achieved such advancements would have also evolved beyond aggression or territorial conquests, we cannot be certain. A civilization might seek resources unique to our world, be it water, minerals, or even something as abstract as information. They might see Earth as a suitable colony, or perhaps a strategic vantage point in a larger cosmic plan. On the more benign side, their intentions could be purely scientific. To them, we might be a curious case study, a species to be observed and documented, much like how we study less developed species on Earth. But even benign intentions can have unintended consequences. An alien civilization might not understand the intricacies and fragilities of our ecosystems, societies, and individuals. It's also worth considering the scenario where they might be escaping some cosmic calamity, or are refugees searching for a new home. In such a case, their desperate situation could make interactions unpredictable. Lastly, their moral and ethical constructs might be entirely different from ours. Concepts of right and wrong, shaped by their unique evolutionary history and societal growth, could vary greatly from human norms. What they might see as an act of kindness or necessity, we might perceive as an act of aggression or vice versa. Thus, the crux of the matter is not just the discovery of extraterrestrial life, but understanding and navigating their intentions, hoping that mutual respect and universal codes of ethics guide our interactions. Imagine for a moment two worlds colliding, not in the astronomical sense, but on the microscopic front. The alien life we imagine often involves technologically advanced beings or massive spaceships, but rarely do we contemplate the minute, unseen life forms they might carry, their microbial companions. Throughout human history, the spread of diseases has profoundly influenced civilizations. When travelers from different continents met, they didn't just exchange cultural and technological ideas. They also unknowingly shared viruses and bacteria. These unintended exchanges led to outbreaks like smallpox in the Americas after European arrival. The native populations, having never been exposed to such diseases, had no immunity. The results were often catastrophic. Now extrapolate this to a galactic scale. Meeting alien life forms might introduce us to entirely new biological systems. These extraterrestrial organisms, whether harmful in their native environment or not, could have unpredictable effects on Earth's biosphere. It's not just about potential pathogens harming us. Humans might have reactions to alien life at the fundamental cellular or molecular level. Proteins, enzymes, or even chemical compounds foreign to our biology might trigger unforeseen responses in our bodies. Conversely, human microbes might pose a threat to them. What's benign to us might be deadly for them. This inter-exchange of biological material might lead to a scenario where both parties unintentionally harm each other despite peaceful intentions. Moreover, these alien microbes, if they find Earth's environment hospitable, might become invasive species. They could outcompete, prey on, or bring diseases to native species, causing ecological imbalances. We've seen the profound effects of introducing non-native species to new ecosystems on Earth. Alien organisms with no natural predators or controls here could proliferate uncontrollably. There's also the aspect of our planet's environment. If these microbes play a role in their planet's atmospheric balance or any other critical environmental process, their introduction to Earth might have large-scale effects on our climate, weather patterns, or even the composition of our atmosphere. Throughout history, different cultures on Earth have experienced dramatic upheavals when encountering another society with vastly different beliefs, technologies, or ways of life. We can look back at instances of first contact between indigenous peoples and technologically advanced explorers as a small-scale model of what could happen on a galactic scale. These meetings have often resulted in misunderstandings, unintended consequences, and even the unintended destruction of one of the cultures. Now let's magnify this scenario to the interstellar scale. Imagine the vast differences that might exist between our human society and an alien civilization that has evolved independently, possibly for millions or even billions of years. The differences in our communication methods, perceptions, emotions, societal norms, and priorities might be insurmountably vast. The sheer act of comprehending and understanding their intentions, philosophies, and technology could be overwhelming, leading to profound cultural shock. We are creatures of habit, shaped by our evolutionary lineage, environmental pressures, and societal structures. Confronting beings who might not share any of these evolutionary or societal histories with us could challenge the very core of our understanding and beliefs. Moreover, their technological advancements could make our most cutting-edge tech look rudimentary in comparison. And just as the indigenous tribes of our world were awestruck and overwhelmed by the technology of explorers, humans might find themselves in a similar position, but on a cosmic scale. This vast difference in technology could lead to a power imbalance. Even if the alien civilization has peaceful intentions, their mere presence and advanced abilities could inadvertently disrupt our societal structures, economies, and technologies. And as always, thanks for watching our video.